Welcome back to Algebraic Graph Theory Seminar. Today we have Jo Ellis-Monaghan, and she's going to be talking about concepts similar to dualities in graphs.
Nice dodge. So this is self-twualities for embedded graphs. Thank you for having me here. It's lovely to see everybody. This is joint work with Lowell Abrams at GW. So let's get started. I'll talk a little bit about why we're looking at dualities of graphs, self-Petrie duals, self-dualities of graphs, and where you can leverage these kinds of concepts. Then, before I can talk about the algebraic structure, I need to talk a little bit about the underlying objects. And then I can delve into the algebra, which is lovely, being at an algebraic graph theory seminar and being able to do that. And then the kinds of big questions that we can answer once we have that algebraic structure. So one of the reasons for looking at self-duality and self-Petrie dual kinds of structures is that they reveal symmetries of graphs. So these are even just some pictures out of Wikipedia. But this on the left is a self-dual graph in the plane. This is the Haywood graph, which if you put on the torus in the right way is dual to K7. This is the Peterson graph with the green vertices and K6 as its dual in the projective plane. So these reveal symmetries of these graphs. The other, and where I came to this, my interests are really in graph polynomials. And I got led down this path to perdition through identities for graph polynomials. So one of the most renowned is the duality relationship for the Tut polynomial. So if you've got a plane graph with a plane dual, then the Tut polynomial just switches the role of the variables when you look at the plane dual of the graph. If you lift to these duality relationships, you get further information. So the four-color theorem is true if and only if, for every connected bridgeless plane graph, there's some subset of the edges so that you can give them a half twist. That's what this business up here is saying. And if you do that, then the resulting graph is not four-face colorable, it's actually three-face colorable. So it gives you an equivalent statement for the four-color theorem, but with three color of those plane graphs, which is very unexpected, but you can't do it without looking at these duality relationships. You can't see that just staying in the plane. Similar thing happens with a polynomial called the Penrose Polynomial. This arose in physics, this beautiful paper, applications of negative dimensional tensors. If you've ever seen Tolkien's drawings, original illustrations for The Hobbit and The Lord of the Rings, the illustrations in here, that's all I can think of, is that they look like Tolkien's drawings. But they're actually little diagrams for dealing with negative dimensional tensors in physics. And from that, there evolved something now called the Penrose Polynomial, which was there defined just for planar graphs. And surprisingly, coming out of this physics setting, turns out to also encode graph coloring in a very different way from the chromatic polynomial. That there are a couple of evaluations that count three edge colorings, and three edge colorings in planar graphs correspond to the four-color theorem. But again, if you let yourself work in this realm of being able to take these duals and twists of graphs, it turns out that this polynomial has a deletion contraction reduction, which you cannot see if you're just looking at plain graphs. And you can also see, which was again not apparent in the original formulation, of why the Penrose polynomial might be encoding coloring information. So it gives a nice expression for the chromatic Penrose polynomial in terms of the chromatic polynomial. Okay, so that was very high level. I don't really expect you to know I haven't defined these polynomials or defined the terms yet. But I just wanted to let you know what the setting and context and motivation were. They let you know stuff for looking at these self-twualities, for the graph symmetries and for the way that they interact with graph polynomials. Okay, so now let's go back to the beginning and kind of do things right from the ground up with all of the explanations now. The graphs that we'll be talking about here are cellularly embedded. So all the faces are two cells. They look like little pieces of R2. If you take the graph out of the surface, so this is an example of a graph that's cellularly embedded in a torus. And this one down here is not, because if you take the graph part out of the torus, what's left isn't a bunch of little pieces of R2, but actually an annulus. So it gets too hard to keep drawing the surfaces and the graphs on them. So there are other ways of encoding the information of a graph that's drawn on the surface. So here's one way. Here's a graph cellularly embedded on the surface. If we take a little epsilon neighborhood of the graph, you get these little disks for the vertices and rectangular disks for the edges. This is called a band decomposition. If you take the faces out of this surface, you're left with something that's called a ribbon graph. And a lot of the drawings, a lot of the ways that I'll represent things in this talk will be as ribbon graphs. This is an example of K4 in the projective plane. And you can go backwards simply by sewing disks into the boundaries of the ribbon graph. That takes you back to the graph cellularly embedded in the surface. All right, even the ribbon graphs get to be a pain to draw after a while. And you'll notice that if you label the edges, if you give the edges names, you don't really have to draw the ribbons. You just have to keep track of where they attach to the disks. So here's the ribbon graph. And if I put an arbitrary orientation on each of the disks and each of the ribbons, and I label the ribbons, this lets me record only the information of where the ribbons attach to the disks and their names. So if I have disks with those ribbons on them, all I have to do is attach head to tail with arcs, and those will give me the ribbons back. I'm going to stop here just for a second, because if this doesn't make sense, the whole rest of the talk is going to blow past you. So does anybody have any questions about the ribbon graphs? You want to just stare at that for a second?
Okay. Maybe I'll ask it. So it looks like there's not going to be any difference between whether the 3 ribbon goes above or below.
Yep.
The other, but
It doesn't matter whether they're which is above or below. It also, up to parity, doesn't matter how many twists are in the ribbon. Right, so I'm only showing one little half twist. Yeah.
Great. Thank you.
Yep. Also, I can just sort of physically flip any of those vertices over, and it will reverse the direction going around it and toggle all the twists. Yeah, exactly. All right. Let's just remember what the surface dual is. This is exactly like taking the planar dual of a graph. You have a graph in a surface, and you stick vertices in the faces. You put one vertex in each face, and you connect two of those new vertices if the faces that they're in share an edge. So there we go. That's the dual, surface dual. Whoops, whoa, stop. How did that happen? Okay, let's try that again. Yeah, it's sort of like when your car starts driving without you. All right. So vertices in the faces and connect them up if they share an edge. So a couple of things to note here. The graph and its dual are in the same surface, but in general have different underlying graphs. This particular example, though, is self-dual. The original graph and the dual are the same graph. Right here, that clearly isn't the case. On the right, the Peterson graph is not K6. They're just duals of each other in the projective plane. Over here, this is another self-dual graph in the plane. So the graph, the blue graph, and the graph you get from putting a red vertex in each of the faces of the blue graph and connecting up the edges. They've got a really nice diagram that makes the isomorphism clear. Okay. All right, lovely. The other thing to notice is that taking a dual has order 2. If you take the dual of the red graph, you get the blue one back. All right, so that's duality. The other operation we're going to talk about are Petrie duals, or these are sometimes referred to as left-right walks. In terms of ribbon graphs, the easiest way to think about it is that you just take each of the ribbons, detach it from at one end, give it a half twist, and stick it back on. It's equivalent to taking a graph and replacing the faces in it by left-right walks in the graph. So if you've seen it in that context, it's exactly the same thing. Couple of things to notice here. The graph and its Petrie dual have the same underlying graph, but in general, they lie in different surfaces, right? So the graph on the left here is in an orientable surface, graph on the right isn't. So they're really on very different surfaces. The other thing to note is that taking the Petrie dual also has order 2. So if you twist all the edges again, you get the original graph back. So those are Petrie duals. All right. Now, these two operations taken together give you a group operation on the whole graph. Something called the Wilson group from back in the late 70s. It's the group generated, you take the group generated by taking the dual and taking the Petrie dual. Those two don't commute with each other. So you get a group isomorphic to S3, and this applies to the whole graph. So if you apply delta to the graph, that's taking the dual. If you apply tau, that's twisting all the edges, that's taking the Petrie dual. Tau delta or delta tau, these don't commute. These are operations of order 3. You have to apply them 3 times in order to get the original graph back. Those are called the Wilsonial or the trials of the graph. And then there's one more operation of order 2, which Wilson called the opposite. And either delta tau delta or tau delta tau, you get the same thing. So far, so good? Yeah. Okay. So we've got this lovely operation applying to whole graphs. And then what people generally are interested are self-twualities. So we need a word to refer to these operations, these 6 operations in aggregate, right? So they're twisted duals, they're trials, they're duals. We call them self-twual, or they call those operations just twuality, okay? And in general, you're seeking graphs that are self-dual, self-petrial, self-twual. See, I can't even get the words out. Self-trial. Okay. So here's an example. This is a blossom graph B2. So just 2 loops on a single vertex. And it's all 3. That graph is self-dual. It's clearly self-petrial. If you twist both those edges, you're going to get the same thing back. And it turns out it's also self-trial. And then there are kind of special kinds of graphs. So not graphs that are all 3, but graphs that are self-dual, but neither self-petrial nor self-trial. So here's, whoop, yeah, it's driving itself again. So here's B2 in the torus. That's self-dual. That's the graph that we saw a couple of slides ago. It's neither self-petrial. If you twist both of these edges, you're not on an orientable surface anymore, so it can't be the original graph. And it's also not self-trial. This graph right here is self-petrial. If you twist both the edges, you get back what you started with up to isomorphism. It's not self-dual and it's not self-trial. This one is the one we saw a minute ago. We call these self-wilsonial. They're self-everything. They're self-trial, self-dual, self-petrial. They're lovely. But examples which are self-trial, this operation of order 3, without being self-dual or self-petrial, are very hard to come by. In fact, Wilson originally conjectured that they didn't exist. So the first example that they were able to come up with is a graph that is you take a tiling of the hyperbolic plane with 9 gons. So you put 9 gons at each vertex. And then you identify vertices connected by left-right walks, the Petrie polygons in there. And that gives you a regular map. It has characteristic -70. It's got 126 edges. It's freaking huge. All right. And that was the only example that folks were able to come up with. And then in 2010, Jones-Poulton came up with a theorem that said that, and all of this work generally was focused on regular maps. So all the vertices have the same degree, all the faces have the same degree. There's a lot of symmetry to work with. That the regular non-orientable examples of greatest Euler characteristics are the ones that we just saw with characteristic -70 and the double covers with characteristic -196. They're huge, right? Then if you look for orientable examples, they're even bigger, right? So these are really symmetric. Transitive automorphism groups, lovely. So why are these things so hard to find? Well, if G is a ribbon graph, and you've got a graph that's self-trial, that happens if and only if the dual of the graph, right? The graph that you get by putting vertices in all the faces and connecting up the edges, and the graph that you get by giving all the edges a half twist, which are two really different operations, end up being the same. So that's a remarkable amount of symmetry. Also remember that the dual is always in the same surface as the original graph, and taking the Petrie dual is always going to give you the same underlying graph. So here is an example of when this does happen. So here's a graph G. If you twist all the edges, you get this graph. So that's what you get if you just take the two twists out of here and put one in down here. So it's easy to see that that's the Petrie dual. It's a little more work to just take the dual and notice that you get exactly the same thing. But this graph is not the same as either its dual, right? These two graphs, the graph on the left and the graph on the right, are not the same graphs. Okay, so this is one of those special graphs, little teeny tiny one, not some great big huge thing. And here's what it looks like in the surface. But this tiny example is not a regular map. So we had to have other tools for finding these. And it turns out there are actually a zillion of these kinds of graphs. But you needed new tools. You needed the algebraic tools to find them. So let's go look for that. The goal is to be able to generate all of those self-trial graphs that are self-trial, but not self-dual nor self-petrial. And in fact, why stop there? Maybe you want a systematic way to find all graphs of any specified kind of self-twuality. Right? Because I'm just a little bit greedy. So that's what we were looking to do. We wanted a systematic way to find these. So here's a fundamental observation. This is a very simple classical result, but it's at the heart of what makes the much more complicated algebra later on work. If you have a graph that's self-dual, so say H is equal to the dual of H, and you have some other graph that's in the orbit of H under the Wilson group. So suppose G is the Petrie dual of H. Then G is going to be self something. It's going to be self tau delta tau inverse. It's whatever H was to begin with goes in the middle, and whatever you did to H to get G is what you conjugate by. And that works for anything in the Wilson group. So if G is anything in the orbit of H in the Wilson group, you get new self-twualities from old by conjugation. So here is a graph that's self-dual. If you take the twist of it, this graph here, this graph is self, if I do twist delta, twist inverse to this, I'll get G back. So the lesson from this is that if a graph has any form of self-twuality, that self-twuality propagates through its orbit in some form. All right. So what we have now is an algebraic framework that's much more powerful. It's going to manipulate each edge individually, and it's also going to handle duality up to isomorphism. And it works by applying the Wilson group operation one edge at a time instead of globally, and by using permutations to track the isomorphism. So let's look at those operations of taking the dual of a graph and taking the Petrie dual as local operations, just one edge at a time. For twist, it's pretty straightforward. You've got a graph, and instead of twisting all the edges, just one of them. This is, it's going to be easier when I go to do the examples. It's going to be easier to do the examples with those disk representations, because otherwise the drawings get too complicated. So to do the twist, you've got an edge EI that connects these two little arcs on the disk. And all I do is reverse the direction of one of those little arrows. Okay, and that's how you form this twist. So this is the disk representation for this ribbon graph. Right, I'm just connecting those two up and connecting these two up. And in order to twist this one, I just reversed the direction on this one edge so that when I put the ribbon back in, it's going to have twist in it. Okay. All right. Taking the dual with respect to an edge. So this is partial duality. Shmutov came up with it, although I'm hearing inklings now that it's possible that some 30 years ago, Boucher actually had this buried in a paper somewhere, but never did anything with it. But let's, Shmutov certainly popularized it, and he certainly showed the power of this operation and what could be done with it. So the intuition here for taking the dual with respect to an edge is when we take the dual for the whole graph, it's kind of like you're taking a perpendicular edge, you're replacing an edge by an edge perpendicular to it. And that's what we're doing here. Instead of this edge where you connect the ribbons across this way, we're going to want to connect them going up and down. So you merge the two vertices and put the dual edge now going up and down. So here's an example. This is this graph, and there's its disk representation. I'm going to take the dual with respect to E1. So in order to do that, I first need to kind of rotate those two disks so that the E1s are facing each other, like I have up here in the general diagram. So I've rotated these two disks, which put the E2s out on the far edge, and the E1 now, this configuration gets replaced by this configuration. And that has merged those two vertices into a single vertex. And if I attach the ribbons back on, this is the graph I get. So if I take the partial dual with respect to all of the edges, as you would hope, this is the same as taking the usual Euler-Poincare duality that we saw at the beginning, taking the dual of the whole graph. So the example on this slide, these two examples are exactly the same example, just in two different notational frameworks, depending on which one you're more comfortable with. You start with this graph G, this triangle. And instead of using numbers, I've used colors to identify the edges. So this is the disk up top is the disk representation for the triangle. And you can see where the red edge goes and where the blue edge goes and where the green edge goes. Taking the dual with respect to the red edge means to merge the two vertices and then relocate the little arrows. And this is the ribbon graph that results if you draw the ribbon arcs back in. We'll do the same thing now for the green. Take the partial dual with respect to this green edge. And, oops, I'm sorry, I lost track of colors. Take the partial dual with respect to the blue edge. Bad Joe. Blue edge down here. Merge the two vertices. You get this with the arcs now perpendicular. And this is the resulting ribbon graph. Doing this last one, merging the green, when you merge these two, you actually now get two circles. And there's the green bit. And what I've done here is, here's this figure, and I've just stretched the two lobes out to bring them close to each other. Right, and there's the two green bits going this way, and now I need to make them go horizontally, vertically. So there they are vertically, and that's where this came from. Okay. And then if I connect the edges back up, this thing here is a vertex, this thing out on the other side is a vertex. You can think of this drawn on a sphere, the other vertex on the far side, and this is the same ribbon graph. These two are both the same ribbon graph. And sure enough, it is the familiar and beloved dual of the triangle, if you take the partial dual with respect to each of the edges. So that's a crash course in partial duality. All right, but now you have the ability to take the dual with respect to the edge and the twist with respect to the edge, which means that both of those together, which generate an action of S3, act on every edge. So now you have an operation of S3 to the n, or m, however you like to count your edges, on the ribbon graph. So what we're looking at here is a copy of K4, and I'm going to apply the full orbit of this ribbon group to this edge that's indicated with a star. So first, I twist it. There it is. It's got a twist in it. Lovely. Now I'm going to take the dual, partial dual with respect to that edge. So I merge the two vertices and I put in the perpendicular edge. Okay. And then I'm going to twist that perpendicular edge. It's a little subtle here, but see this business right here? That's where the twists happen. Right there. And spot the difference between those two in the figure. And you end up with this graph. And similarly, if I take the dual of this graph, you merge the two vertices and put in the perpendicular edge, then you twist that edge. And it turns out that if you take the dual of a loop with the twist in it, it doesn't do anything except for torque the underlying vertex. So there it is. And that's the full orbit on one edge of this ribbon group action on the ribbon graph. And just to get a little more sense of it, there's the ribbon group action. This is the full orbit of applying the ribbon group action to either one or the other or both of those edges to this graph G. So there's that graph G. It's self-petrial, and yeah, so those are everything in its orbit under this ribbon group action. But isomorphism matters when you're taking duals, because sometimes the identification between the graph and its dual is direct. It uses this canonical identification of the edges, and sometimes it isn't. So for example, this little lollipop graph, if you will, if you take the dual of it, the isomorphism sends E to F and F to E. And we call that weakly self-dual. This is weakly self-petrial. If you twist both of the edges, it twists E and untwists F, you have to send E to F and F to E. This graph here is strongly self-dual and strongly self-petrial. If you take the dual, you get exactly this, and you can send E to E and F to F. All right. So here's the algebra that encodes both these partial duality operations and isomorphism. So the objects that we're going to act on, are ribbon graphs with edge labels. And the group delta tau to the n, right, this action of S3 that acts on each of the edges, view that as a sequence of elements that act on the edges in that order, right? So the first element acts on the first edge, second on the second, and so on. But you need to be able to keep track of reordering the edges. So you take a semi-direct product with the symmetric group on n, right? So you've got this wreath product, and an element of this wreath product, so gamma, something out of the ribbon group, and something out of the symmetric group, acts on a graph G with an order of its edges by replacing lambda by lambda pi inverse, and then applying the ith element of the ribbon group to the edge lambda pi inverse of I. Blah, blah, blah. It just keeps track of which edge you're supposed to be applying to. So here's an example. Suppose this is our graph G lambda, and we've ordered the edges 1, 2, 3. And I'm going to apply the element tau, delta to this graph. This is I, this is the identity permutation, because it's hard enough to do one thing at a time. Let's not reorder the edges right now, okay? So this means that we're going to apply tau to the first edge, delta tau to the second edge, and delta to the third edge. And if this had been some wacko permutation, it would just reorder which element of this you applied to which edge. So here's the computation. There's your graph. This is the same graph. I'm just color coding it again. I'm going to apply tau to the red edge. It just changes the direction on one of the arrows. So I changed the direction on this arrow. Now I need to do delta tau to the blue edge. So this is first doing tau to the blue edge. So I've just flipped this arc right here. And now I need to do the partial duality operation. So I first stretch out this circle so that I can put the two blue bits next to each other. Then I merge that, and instead of having the two blue bits going this way, now I want them going this way. Okay, perpendicular. And then I untangle this loop, and it looks like this. So this is the result of applying delta tau to the blue edge, and now take the partial dual with respect to the green edge, doing the same kind of operation, and I get this. And this is the result. So that's how the group acts on ribbon graphs. All right. You know you're really doing an algebra talk when you've got commutative diagrams in it, right? Okay, so here's the strategy. Here's how this works. Now that we've got this algebraic tool, we can use it to get the kinds of self-twualities we want. We put something nice down at the bottom, and I'll talk about how we find something nice to put down here. Then up here, you put your favorite map. You say, oh, I want to find self-petrial graphs, or I want to find self-dual graphs, or I want to find what we were originally looking for, these self-trial graphs. So you put that here. You put delta, delta, delta here, or you put tau, delta, tau, delta, tau, delta here. And then you solve this business right here equal to the thing that you want. You solve that for alpha. And once you know the alpha, you already knew what H was from this nice thing down here. You apply that to H and you get your G here that will have the nice duality property that you're after to begin with. So this is very sweet. And solving for alpha turns out to be easy. It's lovely. All right. So the real question is, how do you get what goes on the bottom of this map? How do you get something nice here that lets you run this operation? So this is the thing of beauty. It turns out that every connected ribbon graph has somewhere in its orbit a single vertex orientable ribbon graph. Because you can take this triangle and remember that taking the partial dual with respect to an edge merges vertices if they're separate. So it just sucks vertices together. So you suck all the vertices together until you've only got one vertex left. If any of those loops have twists on them, you just untwist them. And there you go. And if you remember from way back when, we discovered that any kind of self-twuality anywhere in the orbit propagates through the whole orbit. So if we know what's going on with this little, really easy little guy here, this little one vertex ribbon graph, then we know what's going on in the entire orbit. And so you just write, actually Lowell did a lot of this, right? Just the code that finds all of the self-duality properties of one vertex ribbon graphs. And the wonderful thing is that one vertex ribbon graphs are just, they're just chord diagrams. And chord diagrams have dihedral symmetry. And so you're only checking dihedral symmetry. You're not checking for graph isomorphism when you're looking for self-twuality properties. So that's what you do. You put the chord diagrams in canonical form, you remove the duplicates, and then you look at these irreducible single vertex graphs and consider just those and use them to find all self-dual, self-petrial, self-trial, self-what have you graphs in the single vertex orientable graphs. So we just generate all of them, test them for self-twuality, and it's really quick to solve for A. You're just going through the cyclic group. And then the output is graphs with the desired twuality property. So down here, we start with the graph G that we're interested in. We suck it down to a single vertex. We look at that single vertex graph and look for any kind of self-twuality, anything. Okay, and again, looking for that is just looking for doing a search on symmetries of the dihedral group. Once we found that, we put that down here. We put the thing we want up here, and we solve to find out what the G is that has the property we want. So there it is. For each of those single vertex graphs, you find the stabilizers, and then you play. This was way fun. So you want a self-trial graph with 3 edges? No problem. You start with any 3-edge single vertex ribbon graphs, find a stabilizer, and then solve for A. Solving for that A is iterative, and it's bounded by 6 times the number of cycles in the permutation. So that comes pretty fast. So here's an example. Here's the graph. It's a one vertex graph. It's, if you don't do anything to the first edge, You take the duals of the second and third edge. This thing is self, whatever that kind of duality is. But we want something that's self-trial. So you solve what you get from here for alpha. And that gives you alpha being tau, delta, delta. You apply that to this graph here, and you get this. Voila, this graph is now self-trial. It's different from the one that we saw before, and there are 5 other solutions. And then we just did this exhaustively. The net was a complete list of all self-trial graphs for each number of edges. I don't remember where we stopped looking at it, 8 or 9 edges, but there are tons of them. And you don't need to be up at 126 edges to have graphs with these kinds of symmetry. But why were they finding these with regular maps? Why was that such a rich hunting ground? Well, it's because those regular maps have ginormous automorphism groups, and you can use the automorphism groups to do this. So instead of down in the bottom here, fooling with the self-twualities, you can play with elements of the automorphism group. Really sweet. So down here, you take any graph at all, any element of its automorphism group, and of course, the richer the automorphism group is, the more you can play. You put the thing you want up here, yay, and solve for A. There's one restriction. You got to make sure that A doesn't have the wrong kind of symmetries. It doesn't interact with that automorphism group element in the wrong way, but that's pretty trivial. And so, yes, in general, you're going to get a lot of nice kinds of symmetries out of groups with large automorphism groups, graphs with large automorphism groups. So here's the last example here. This is a lovely group, a lovely graph with a lovely automorphism group. So let pi be the automorphism that spins it 1/3 of the way around. Solve alpha pi inverse equal to the thing that you want, right? This triality thing that was kind of our goal. Delta tau, delta tau, delta tau, delta tau. What we want. You solve for alpha, you get this. You do this weird thing to here. Voila. This graph is now self-trial. It's got a loop, so it can't be self-petrial, and so it can't be self-dual either. So this is another one of those special graphs, and you can get them really pretty easily. And that process extends to an infinite family. You can play that game with more and more loops. So there are lots and lots of self-trial graphs that are not self-dual or self-petrial. They don't need to be regular maps. They can have very small characteristic in genus. So the take home here is that there are now systematic algebraic tools to study self-twuality, getting any kinds of self-duality, petrality, triality, whatever, on any graphs, not just regular maps. That information is encoded in single vertex orientable graphs. You really only need to study one vertex graphs. And you can use one vertex graphs with any kind of self-twuality to get the self-twualities for any of the graphs in their orbits. Or forget the one vertex graphs, just grab the automorphism group of any graph to solve for self-twual graphs to get the desired type of duality in its orbit. So that is way fun. Thank you very much.